Hi, my name is Michal, and for the past 2 months I've been working in the Robotics lab at Carnegie Mellon University. I'll be talking about the vehicle routing problem with floating targets and how to solve it to prove an optimality using branch, price, and cut. In the classical vehicle routing problem, every customer sits at a fixed location. The floating targets variant relaxes that. The targets are mobile. Each one can move away from its home at its own bounded speed toward whatever meeting point is convenient. So the vehicle and the target cooperate on where to meet. That means that the set of places a target can be picked up isn't a point, it's a disk that grows over time. The routing decision is coupled to a continuous choice of meeting points. So a fleet of K vehicles with capacity Q leaves a depot, serves the target, and finishes at the drop-off. We minimize the total fleet travel time subject to capacity and the speed limits on both sides. This comes up in last mile delivery, where a customer walks in a rendezvous point, in ride sharing with pickup within walking distance, and in mothership daughter systems, where a carrier recovers small agents that can't make it back on their own. Our approach is branch, price, and cut over a route-based reformulation. Instead of the compact model with position indexed variables, we write one binary variable per feasible route. Theta r is 1 if route r is used. The cost CR is the travel time of that route. AJR says whether route R serves target J. We need every target covered, and we can't use more routes than we have vehicles. The payoff is that the second-order cone constraints, the ones tying meeting points to travel times, disappear from the master problem entirely. They get pushed into the cost of an individual route, where we handle them exactly. The catch is that the number of routes is exponential, so we can't write this problem down. That's what the rest of the algorithm is about. Here's the structure. On the outside is branch and bound. We relax integrity, and when the solution has a fractional arc, we branch. One child forbids the arc, and other forces it. Inside each node, we solve the linear relaxation by column generation. We keep a restricted master problem with only a subset of routes, solve it, get dual prices, and then ask a subproblem whether any routes outside that set would improve the solution. If yes, we add it and resolve. If no, the relaxation is optimal for the full set. At the root node, we also separate cuts, which tighten the relaxation, which means a smaller branch tree. Cuts are basically valid inequalities that allow us to limit the search space. The bottleneck in all of this is the pricing subproblem, so let me spend the rest of the time there. Pricing asks for a route with negative reduced costs, a tour that would improve the current solution. Formally, it's an elementary shortest path problem with resource constraints, and we solve it with a labeling algorithm. A label represents a partial tour ending at some target. It stores which targets have been visited, bounds on the time of the last meeting, and the dual value collected so far. Extending a label means appending one more unvisited target. We process labels in a priority queue, best first. The problem is that the number of labels grows like n to the q, so pruning is everything. We use two rules. The first is a completion bound. From a given label, count the best prices that the remaining capacity could possibly collect, and if even that optimistic estimate can't reach negative reduced cost, discard the label. The second is dominance. On the right, this is the harder one. Because the targets are mobile, appending the same sequence of two different partial tours can cost different amount, since each one indexes its own meeting point inside the growing disks. We handle it with two closed-form bounds, delivered from the disk geometry. A lower bound on the earliest possible meeting time from the triangle inequality between target homes, and an upper bound from an explicitly constructed feasible schedule where the target walks straight at the vehicle. Then the comparison is this. Both labels meet the same target, so both meeting points lie in the target's disk, which bounds how far apart they can be. If the first label's vehicle can finish cross that gap, the purple bridge in the figure, and arrive no later than the second label's earliest possible meeting time, then it can simply wait there and replay whatever the second label does, for no more cost. In the figure, that's 560 against 562, so the second label is pruned. It's a single scalar comparison per pair, no pre-computed tables, and it never discards a label that could lead to a better column, so the search stays exact. On the benchmark instances from the literature, We match every published optima value, which confirms exactness, and this is log scale. The speedups are frequently 1 to 2 orders of magnitude against the exact dynamic program. The gap widens with vehicle capacity, which is exactly where the reformulation and the dominance rule by the most. On the last instance, the dynamic program doesn't finish at all. Thank you so much to the Biorobotics Lab and RIS organizers for making all of this possible.